Presentation about unsupervised dependency parsing.
Okay, so good afternoon. I will talk about unsupervised dependency parsing, which is part of my PhD thesis. So this is the outline of my talk. First I will introduce what is unsupervised parsing and what are the advantages and disadvantages of it, and some about the problematic evaluation of it. Then I will describe the current state-of-the-art methods of unsupervised dependency parsing. I will describe the Dunn-Klein's dependency model with variance. And then the second half of the talk will be my work. I will introduce the reducibility feature, which is quite useful for unsupervised dependency parsing, then my dependency model, and I give sampling and some results I've achieved. So, supervised dependency parsing, you all probably know it. For supervised dependency parsing, we have some manually annotated tree bank, which is a kind of set of example dependency trees. On this tree bank, we train a parser, and if we have some new text or new sentence, we can use this model and get a new dependency tree. So it's how we know it. Whereas the unsupervised dependency parsing, we have no manually annotated tree bank. We have only large amounts of text on which we would like to induce somehow the dependency trees. So induce based on the raw text or based on the raw text that are possible that they can be protected. So the technical.
So for parsing, you can use also the testing data as training. And we are not cheating. So, why should be unsupervised parsing useful? There is one big disadvantage. So far the results are not as good. Of course, supervised methods for check with only 50% of score versus 85%. Of supervised parsing. For English, the best unsupervised parser has about 60%, whereas the best supervised parser about 90%, I think. But the advantages are that we don't need any manually annotated tree bank, which is quite expensive and time-consuming. We can parse possibly any language in any domain. So if we get some new language and we want to parse it, we use the unsupervised parser and get some possibly good enough trees. And we don't depend on text set or tokenization. We use only text. We get the text, run the parser, and have the trees. There is some analogy with word alignment, because dependency parsing can be also seen as alignment of a sentence with itself. Where on this example we align the sentence with the same sentences. The connecting word to itself is disabled, and then it is same as for alignment. We connect for each word. We find its counterpart, which is the parent in a dependency tree, and we can attach the word to the root, which is equal to alignment to 0 word in word alignment task. For word alignment, there exists the Giza++ tool, which is quite very widely used, unsupervised tool for word alignment. And why it is so widely used? Maybe because it's very easy to use. It works on any corpus. If you have parallel corpus, any parallel corpus of any languages, we can run Giza++ on it. And if we have large enough, if the data on which it is tested are large enough, the quality is very good. So maybe Similarly, it should work with parsing,
One more thing, maybe if we would have, if we had parallel corpus which is manually annotated, some larger parallel corpus, I mean, for example, 1 million of words, we should have some supervised tool for word alignment that would have better results than Giza++. But we don't have it and nobody needs it, so maybe it's quite enough to use unsupervised methods. So why it shouldn't be used for also for parsing? Oh, that's about the metrics. If we evaluate unsupervised dependency parser, we can simply compare it with some annotated data, as we do for the supervised parsing. The problem is that if we do some linguistic annotation, we have to make a lot of decisions how to annotate some problematic notions or problematic phenomena, like how to attach auxiliary verbs or how to attach modal verbs. Whether one modal verb should be above the main verb or below the main verb. What to do with coordination structures or prepositional groups, how punctuation, everything. We have to decide, the annotators have to decide somehow to annotate it. And this is not fair for unsupervised parsing, because unsupervised parser can handle them differently, this phenomena. Can decide that, for example, that auxiliary verbs will be below the main verb, and in the tree bank it is in opposite way. So it's quite the scores for the unsupervised parsers are automatically lower. At least, for example, punctuation. In PDT we have all the punctuation, I mean full stop, is attached to the technical root, but unsupervised parser attached to the main verb, for example, which is also correct, but we have about 5% lower score. Often there are used two metrics are used. Unlabeled attachment score, which is the standard score for dependency parsing, and undirected, where the edge direction is disregarded. It is not a mistake if governor and dependent are switched. It's a kind of simplification, or someone used this score, but however the most common is what unsupervised dependency parsers, what people doing unsupervised dependency parsing use is the common attachment score. Ideally, the parsing quality should be measured not intrinsically, in this way on some application. For example, machine translation on question answering. I think that there exists some machine translation tools which use the unsupervised parsing and are quite have some very good results. So this is the evaluation. So now I will describe some current methods which are used mainly in Stanford University. And something about history. First approaches were based on pointwise mutual information between two words in a sentence. It was before the year 2000, and these approaches have problems in being better than the simple right and left baseline. What is right baseline? Right baseline is that every word is attached to the following word. So it is like right chain. It's like a string. The left baseline is opposite, that every word is attached to the previous word. In 2005, Dan Klein introduced in his dissertation the dependency model with violence, and which was very, very important, and it is used until now in the state-of-the-art methods for unsupervised parsing. So the dependency model with violence is a generative model, and the generative story is following. For each node, it's a recursive generative story. First we have only the head of the sentence, and then we will generate all its left children, one after another. And when we generate all the children to the left, we generate the stop sign. Then we start generate all the children to the right, and then generate the stop sign. And this is a recursive process. So after if we generate a child, we generate all its children and go deep to the recursively to deep. So in this case, we have the VB, which is a verb, English verb. We first start generating words to the left, so we generate the noun, recursively go deeper to the noun and generate the first left child of the noun, which is a determiner. And determiner, the generative process decided that determiner has no children to the left, so it generates the stop sign. It decided it has no children to the right, the other stop sign to the right, and go recursively back. And in this by that algorithm is generated the whole dependency trees. In dependency model, equivalency is projective. It generates only the projective trees, and yes. So in this dependency model, it has two parts or two different probabilities. Yes.
Is this sorry to interrupt, but is this a process to generate random sentences, or do you have the nodes given, or?
Yes, it is a generative story. In fact, it is not generated in the algorithm. We only use some generative model which can generate possibly any sentence, and this model is then used for maximizing the probability of the tree bank. We only want to have some model of the dependency trees, which we will somehow maximize. This concrete model is maximized by in Klein's dissertation. They used the simple EM algorithm. It's a variant which is inside-outside algorithm for dependency trees. So this is the description of the dependency model equivalence, where the probability of stop given the post tag of the head, the direction from the head, and adjacency, whether it is the first child to this direction or the other child. And P choose is a probability of generating A, which is a part of speech tag of the children, given the part of speech tag of the head and the direction. And this is the formula for probability of the subtree, which is governed by the head H. So we multiply this is the generating of children. We don't stop and generate children, and after generating all the left children we stop, and after generating all the right children we also stop. I don't know whether it is clear, but so it was the basic dependency model equivalency. Then it was extended that the probability pages can be based for the generating A. For the generating the argument A, we use also the adjacency. We use lexicalization, so we don't use only the part of speech text, and we use also the word forms, and there are some smoothing
And here's the table of the progress from 2005 to 2011. So the random baseline, it is measured on English Pantry Bank, on the development data, which is World Street Journal 23. And the random baseline for English, I mean generally non-projective trees is only 4%, left chain 21, right chain baseline, this is only the baselines, 29% is the right chain for English. And the dependency model equivalence in 2005 had only 35% on Pantry Bank, then the extended model in 2009 42, and then it went up, and this is the state-of-the-art results, and by Valentin Spytkowski in 2011, who have 58% on Pantry Bank. With this quite simple model. So now I will switch to my experiments. I introduced the new feature into the model, which is the reducibility feature, with which we should recognize which words are dependent or which words are. If we have a large text, we can recognize which words are leaves or which words tend to be root, and like this. I will introduce the 4 submodels of my model, and I will describe the Gibbs sampling algorithm and how I automatically induce the dependency structures. So first, the reducibility feature. The problem is whether we can somehow recognize only from text which words are dependent or which words will be leaves in the dependency tree, which word will be more heads. The definition is that a word of a segment of words, by segments of words I mean the n-gram, the word is reducible if the sentence after removing the word remains grammatically correct. A hypothesis is that reducible words or reducible segments are leaves or subtrees in the dependency tree, which is not true for every word, but at least for adjectives and adverbs. It's true. There is some example. It's not very good. If I have a sentence like I like yellow bananas, and I want to know whether the word yellow is reducible, I remove it from the sentence and I check whether I like bananas is grammatical. I like bananas is grammatical, so the word yellow is reducible. The problem is that we need to automatically recognize which sentences are grammatical, so it's quite a problem. But if we have a very large corpus, I mean large enough, we can search for the needed sentences. So, if I have a sentence in the tree bank, I like yellow bananas, and I want to know whether the word yellow is reducible, I can try to search for the sentence I like bananas, whether it is in the tree bank, it is in the corpus. And if it is there, it's possibly grammatical. Of course, in the corpus can be everything, but it's quite likely that the sentence is grammatical. If it is not in the corpus, we don't know, because majority of sentences are not in our corpus. However, we would like to assign some scores to every part of speech tag, for example, or every segment of part of speech tag, some score which says whether this part of speech tag is reducible or not, or how much it is reducible. And we would like to have, for example, for adjectives and adverbs, we would like to have very high reducibility because they are reducible, they are leaves in the trees. For verbs, we would like to have very low reducibility. For nouns can somewhere they can be reduced because they are leaves. Somewhere they cannot if they have some modifiers, for example, adjectives, and so on. So how I compute this reducibility?
if I have a part of speech tag or part of speech sequence, n-gram of part of speech, for example, preposition noun, the bigram preposition noun. And so I go through the corpus and search for all these bigrams, preposition noun. And for each such occurrence, I remove the respective words, the two words which are preposition and noun. And I check in the corpus whether the rest of the sentence, which remains, is at least one somewhere in the corpus, which means whether it is grammatical or not. And if so, then such sequence of words is reducible. If not, it is not reducible. And I denote RG, but by RG is the number of all reducible sequences in a corpus, and the CG is number of all sequences. Of course, the RG will be very little number, because we don't have all the sentences in the corpus, and CG will be very quite high number. And the reducibility is computed simply by dividing the number of reducible sequences by the number of all sequences in the corpus. Here, the 1 over n is the normalization. The normalization is something like average reducibility in the corpus of all through all the sequences, probably. And I do some smoothing here, because I don't want to have zeros there, because I cannot say that something, if it is not reducible at all in the corpus, has a zero reducibility. I don't know it, so I do the smoothing. And also for some part of speech tags that are not very frequent in the corpus, it's quite high probability that they will not be reduced, can be reduced anywhere in the corpus. So I don't want to have zero probabilities. So, if I compute the reducibility as I described, here is the table of the most frequent onigrams, bigram, bigrams, and trigrams in the PDT. And as a post tag, I used only the first and second position of the PDT tag. And if you see the unigrams, you can see that the highest reducibility has the adverb, the B, then the punctuation, adverb, the G, adjective, I don't know what is it, this is pronoun. Whereas very low reducibility has preposition, verb in the past tense, verb, it's infinitive, maybe. So it's quite good result. Also for the bigrams, very reducible is the bigram preposition noun and the bigram preposition adjective, which is also very common in a tree bank. The reducibility is very low. Here it is rounded to 0. Similar for English. The adjectives, adverbs has very high reducibility, whereas the verb, the particle to, preposition, verb in past tense is quite. Of course, there are mistakes here, but we can use it for inducing the dependency trees. So now I will describe my model, which consists of 4 submodels, which are edge model, fertility model, distance model, and subtree model. For simplification, in my experiment I used only part of speech tags. I don't use short forms at all. And I induce only projective trees, because it's quite a valuable constraint for inducing the dependency trees, because there are not much non-projectivities in Czech or in whatever language. My generative story is that first I have a root. I will generate the head of the sentence, And after generating every node, I will first generate its fertility, which is the number of its children, number of children which are on the left, and the number of children which are on the right. And then I will generate the individual children. So the fertility will generate the number of children, and the edge model will generate the individual part-of-speech type of individual nodes. So first, I will generate the fertility of a verb. Then I generate first child, which is a noun. I generate fertility of noun is only 1 to the left, for example, and I generate the determiner. And the fertility of the determiner is 0. Then I go to the second child of the verb, and this is the adverb, and fertility of adverb is 0. I go next to the preposition. The fertility of preposition is 1 to the right. I generate noun, fertility of noun 2 to the verb. Determiner has the 0 fertility, adjective 0 fertility, and at the end I generate the first, which has also 0 fertility. And by this generative model, I generate the full. It is a little different from the dependency model with violence. So now I will describe individual models. The edge model is simply the probability of tag of the dependent given direction and tag of the parent. Here I use the Chinese restaurant process, which means that if this particular edge is very frequent in the past, it's more likely to be generated again. And beta here are Dirichlet hyperparameter, which is needed there because it's something like smoothing, or it's if I have generated only the first edge, I have only one edge, and after if I use this model, I had to generate it again if I don't have here this smoothing. I don't know whether it's clear, but. For the fertility model, it's similar. I generate the number of children given the part-of-speech tag. It's similar. It's a bit more complicated here. I use the prior probability P0, which says that the lower fertilities are more probable than higher fertility. The fertility, if the fertility of 10, if it's less likely to have for node to have the fertility of 10 children than only 1 children. So I use some prior probability, which is set to 1 over 2 to the power of number of children, or. And the third model is the distance model. It's very simple. It only says that longer edges are less probable. So it is 1 over the position of parent minus the position of the child, and to the power of gamma. Gamma here is some hyperparameter which is the something like the weight of this model. And epsilon d is only the normalization constant, so that it sums up to 1. And the last model is a subtree model. And subtree model here we use the reducibility feature. So it is the probability of the subtree. The subtree is the node. A subtree of a node I is this node and all its descendants. And it's said if this subtree, if the reducibility of this subtree is high, the probability will be also high. So it is, and the delta is the weight, and epsilon is the normalization here. So this is very important model because it introduced the reducibility feature. And by this model,
it can be easy learned that adjectives are leaves and verbs are the roots and so on. And we want to, for the Gibbs sampling and for the inference of grammar, we want to compute the probability of the whole tree bank. And the probability of whole tree bank is that we simply multiply over all nodes in the tree bank, we multiply all the models. So we go through all nodes or all words in the tree bank, and this is the probability of fertility of the individual or the particular node given. Yeah, this is the fertility of the node times the probability of edge between this node and its parent. This is the parent and direction times probability of distance between this node and its parent times probability of subtree of this node. So if we have any generated tree bank on our corpus, we can compute the probability using this formula. So now the Gibbs sampling. Gibbs sampling is algorithm, iterative approximation algorithm which helps with searching for the most probable solution. So this Gibbs sampling is often used in unsupervised machine learning, and it works as follows. First, if we have a corpus, and first dependency trees for all the sentences are generated completely randomly, random initialization of the dependency trees. And we can compute the initial probability of the tree bank we have, which is of course very low. And then we keep doing small changes in the tree bank. And the small changing is that we pick a node and we randomly change the dependency structure in its neighborhood somehow. It is not the randomly means that it is not uniform, but it is the weighted coin flip. We choose the change by weighted coin flip because the changes that leads to higher probability of the tree bank are more probable than the changes that lead to lower probability. But of course we can decide that we can change it to some very non-probable solution. But the changes that leads to higher probability are more probable. I will show it in the next slide. And after more than 200 iterations, iteration is that we go through all the nodes. We change, we do the small change for every node, and after 200 iterations, the dependency trees converge to some shapes. In this case, after 200 iterations. Now I want to describe the small change, how it is made. For the small, because I sample only the projective trees, I will use the different notation for the description of the small change, and I will use the bracketing notation of the projective dependency trees. This is the example. This dependency tree can be written as this bracketing. Each pair of bracket belongs to one node and delimits or its descendants from the rest of the sentence, and each bracketed segment contains just one word that is not embedded deeper, and this is the head of the segment. For example, here we have the bracket dt and n is not in brackets here, so it is the head of these two nodes. And the head of all the sentence is VB, because VB is not in the brackets. So this notation we will use for the description of the small change.
And the small change is following. We choose one non-root node and remove its. We have the example, and we choose one non-root node. In this example, for example, it will be the VB, which is a verb, and we remove the appropriate bracket. So it is this bracket, and we add another bracket, another pair of brackets, which doesn't violate the projective tree constraints. So we have eight possibilities how to add the new pair of brackets. These are these. In these 4 possibilities, the verb, the preposition will be the head of the sentence, and in these 4 possibilities, the verb will be the head of the sentence. So we have these 8 possibilities how to make the small change. And we can compute the probability of the whole tree bank for each possibility. These numbers are only example numbers. In fact, the numbers are very, very low because we have quite high, tree bank is very high and the numbers are very low. And now we choose one of these possibilities by weighted coin flip, which is weighted by these numbers. Of course, normalized. If you normalize this number and toss a coin, or not coin, toss a octadder, weighted octadder, we choose one of the brackets. We choose this one, which is not the highest, but it's quite probable. So the new brackets will be in this example we will choose the same brackets as we removed, but it's okay. It's okay. We can choose any bracket we want. So this is the small change. And after, for example, 200 iterations, which means 200 times number of words in the corpus, small changes, the tree bank is converged. And what we do with the tree bank? The simplest possibility is just pick the tree bank as it is at the end, and we have the tree bank. But these are problems because the last changes can be not very probable in some cases. So we can do some averaging of the last, for example, 100 iteration. We can compute the edges, the individual edges in the tree bank for for all the 100 iterations, and then use for example, maximum spanning tree algorithm to get the average dependency trees. If we use this maximum spanning tree algorithm, we can get non-projective trees, but why not? So this is the end of description of the algorithm, and these are results. So I use the Conolala tree banks from 2006 and 2007 test data, and I computed direct attachment scores on it. And I compared the result with results by reported by Spitkowski 2011, which is possibly state of the art, but we don't know because many papers present the result only for English, which I think it is not very fair, because not fair. They can be very good, the parsers, but if they have good result for English, doesn't mean that they have good result for other languages. So the comparison is with Spitkowski because he reported the result.
I saw that it was like you presented something like figure 9.
Yes, yes. This is a different data because it's Conolala data, and yes, the results reported by it was Spitkowski, but it was his different paper, and in that paper he reported only the results on English. So in that slide, it was the highest result for English.
Okay, so that's getting the paper actually could, or when you read this particular parts, it would be very friendly more than
Probably. I don't know, because he didn't report the result on all over the languages. This is quite a problem, because if you see the results for different languages, you have one parser which is good for these 5 languages, you have other configuration which is good for other languages, and for the first languages that is completely bad. So it's quite a problem to evaluate this. So I can compare it with this is the last results on Conroll data.
I have one question regarding the evaluation, right? You said something that evaluation changes. Well, generally, there are some errors in it that might not be significant. I mean, you don't attach something particular, but still it has meaning. If you realize the scoring, what is your feeling about this result? Would it be very significant, like 10, 20%?
Yes, possibly 10% maybe, 10%, 15% maybe. It depends on language, and it also depends on because we use here the part-of-speech tags. There are some papers that don't use part-of-speech tag, but then use the unsupervised part-of-speech tagging or unsupervised word clustering, and the results are also quite very good. And these results depends on the text that used. If I, for example, if for Czech I use the fifth position, which is case, the results are much better, because if I use the case, and this is similar for other languages. For example, in German, the auxiliary verbs are differently tagged from the finite verbs, and it makes a lot of differences in. So it depends on mainly it depends on the text set. So it's a problem. And on many papers, the results are using the part-of-speech text, supervised part-of-speech text. But I think the last years there were some papers which report results without the part-of-speech text. I mean, completely unsupervised parsing, only from the raw text. Oh, by this table, I would like to say that my results are better than Svitkowski. We have 18 languages, and for 13 of them, my results are better. And so it's good. But it's a little bit unfair comparison, because Svitkowski used only the Conroll training data, and I use the larger tree bank, not tree bank, the larger corpus. I use the Wikipedia text for inducing the reducibility. Because for inducing the reducibility, I need very large corpus. And this result, the Svitkowski results are not very, are only on training data of the Conroll tree banks. But I think if we have it, why don't use it? So here are some examples of how looks the output for Czech tree. So in this parser, we used only this part-of-speech text, not the word forms, and you can see there are mistakes. Yes, this is this poháru mistrů evropských zemí should depend on zápas. And v nizozemském Hilverstromu should depend on maybe also on zápas.
Did you try to sample from your model, or actually estimate a probability model from parsing and sample from looking for random accuracy?
No. No.
Because you tell you maybe the best parsing of random sample is not the best possible. If you look into the distribution of the possible output, you might see actually something that is the correct parse trees are in the top 20 of the example.
Yeah. I didn't do it, so. Yes, here's the example for English. So it's here's the badly attached the determiner I don't know why. I don't know. And yes, this hoping should be reliable, should be attached to hoping, I think. And 2, we don't know whether 2 is below the rebuilt or un.
Regarding the article, maybe it is the reason because of sampling, right? And if it's part of the case, the sample just doesn't like the situation. You can reparse all of them with your probability model.
Yes.
And you pick the most likely.
Yes, of course. Maybe this is the. Yes, the people who use the dependency model with variance, they use variational bias for inducing the grammar, and they induce the model, and then they do the parsing on. They can do the parsing on other data, and so maybe it can be better. So that's all. One conclusion that. We have unsupervised parser, which we tested on 18 different languages, and we achieved high attachment score for 13 of them. So, thank you.
Thanks to the speaker.
So, questions, please.
I mean, we already had some questions about what you can do, because probably there are many choices what you can do with when you kind of finish your training and you actually have a tree bank, whether it's averaged or not. But then you can imagine to retrain it on those data by using any type of parser. And what you said last was that some people did it like this, right? Like even
they use the dependency model with variance. They induce the probabilities for the as I showed P for the P attach and P stop, and using these probabilities they parse the tree bank. Because EM you don't get the tree bank. Using EM you don't get the tree bank because you get the probabilities.
Okay, so maybe just a technical question. For the comparison, so I understand that actually this is not really kind of really one-to-one comparison with the Spitkovsky. Can you re-implement the Spitkovsky and do the same thing on the large data so that he can, so he also uses the Wikipedia data?
No. Yeah. He don't use it. Yes, yeah, I can do. The problem is that it's quite complicated to implement the inside-outside algorithm with all the things they have there.
But you can use only data he actually was using, right? This kind of sort of data he used, so you don't have to implement his work, but you can do around the same experiment as he did.
But I understood that for the reducibility, you would be disadvantaged because for small data you can't read it.
If I use, I tried it. I tried to infer the reducibility score only from the training part of the kernel tree bank, but there are two bigrams reducible, or 2 words are reducible because it's nothing. I need a large corpus for this.
Maybe you can ask him just to, please rerun it on this data.
Yeah, I can ask him. There will be a challenge. It is a shared task in unsupervised dependency parsing. It is in Montreal with Enako, and I plan to participate on it, and I will meet there all these people. So.
Could you please explain once again why that are
that reducible sequences if you can reduce some segments from the sentence, it's probably it is the subtree, because yes, there are some contra examples, of course, but I don't know. It's not clear, or
Yeah, now that you say I see. Yeah, thanks.
So I wanted to ask, how much does the reducibility bring you? Like, if you're out the reducibility model?
quite a lot. It was, without the reducibility, it is something like 29%. With the reducibility, is 48. And there are some languages that are better without the reducibility. Because it depends on the part of speech tag. If my first experiments were very easy, and I have switched the probability. I didn't use the probability of child given the parent, but the parent given the child, and I get a very high score for Spanish, and that was because the verbs, the tags of verbs were very There had only a few tags for verbs, so that the tags for verbs were very frequent, and they went to the root, and less frequent words went to the leaves. So that's why the attachment score was very high, because it depended only on the text abused.
And one more question to the reducibility itself. So you said that you search for the whole sentence.
Yes.
Some years ago, when I first read the dependency analysis by reduction paper, I also tried a similar thing, not with the Gibbs sampling, nothing, just trying to find out which words can be treated as leaves and which are more core to the sentence structure. And I used the n-gram language model over forms, assuming that if an n-gram of words is very probable in the language model, then it is probably not reducible, or it is grammatical. So So you have a say 4 gram, and you are wondering whether the second word can be dropped or not. So you drop it and check what is the probability of the trigram.
Yes.
And if it's sufficiently high, you say, okay, this is reducible.
Yes, I tried this.
This doesn't work. For me, it didn't.
Mainly in Czech, the problem is with verbs, because you have the three-word order, and verb can be almost everywhere in the sentence. So if you have a noun phrase or prepositional phrase, verb, other noun phrase, and you drop the verb, it's very probable because verb can be everywhere, and
so the model assumes that you have just not seen this verb in this n-gram, so it's somewhere else in the sentence.
That's why I search for the whole sentence, because in the whole sentence the verb must be somewhere.
So do you know the statistics of like the sentence length that are used to confirm? I'm surprised that you learn the trees for arbitrarily long sentences, but not surprised. But that's a great thing that you are able to induce trees even for very long sentences, where I assume that the reducibility was in fact trained on just short sentences because they were easier to find in the corpus.
But I only from the reducibility I only measure the reducibility of individual text. That's all, and I get only this. I take only this scores to the parser and use only the reducibility of the. I don't use the words.
So this is something that you should sell more. That from shorter sentences you are actually able to learn statistics that then apply to longer ones. This is something very very interesting. I feel. And it would be interesting to support this with numbers like how long the sentences are that you are able to validate and so on. Yeah, so thanks for the great talk.
I have just a remark to the comparability of text sets that
Have you thought about using universal text set introduced by guys from Google, Petrov and Damian Das? Have you heard about it? Universal text.
I don't heard about it, but in the share task, which will be in an ACL, there are also some universal tags. Text about 10 texts or even yes, nouns, verbs, adjectives.
Yeah, shared among 20 or 30 languages.
Yes, maybe these are these texts.
This would make the maybe results between languages more comparable. And just to try whether those text sets are as universal as they claim. So, okay.
Of course, the clear solution of unsupervised parsing should be using the unsupervised tagging. Of course, because if you have an unsupervised, if you have supervised parser, if you can say yes, these words are verbs, these words are nouns, and nouns will be attached to verbs, and adjectives will be attached to nouns, you will get much higher results only with this information. Because these completely unsupervised parsers have problems with what is verbs and what are nouns.
Just from the table, when you have all these languages, I noticed that actually you get worse in for the Romance languages, with the exception of Spanish, where it's kind of the same. So have you looked at why? If there is any feature of these languages which, might.
Yes.
Yeah. So you see, Catalan, Italian, what else? There was one more. No.
Basque is not Romanian.
Basque is different.
I try to invest what are the errors in Basque, but I don't understand it at all. I don't know. The texts are completely.
And what about the Catalan? It has so high score in the first case as in no one else.
It depends. It depends on the model. When I try to use different models, the scores for Catalan was higher. You change model a bit, you change a fertility model that you, for example, for the fertility model, I can have the probability of all the children given the head, or probability of number of left children and right children given the head, and if I change it like this, the scores completely change. So, I think it depends mainly on the text set here, because.
If you run the git sampling many times, 10 times at least for all the languages, do you get what is the standard deviation?
Yeah, the standard deviation is about. Yes, I don't have it here. I should have it here. It's about 1%.
So the trees. Do the trees have similar errors across the various runs, or it can also be that you actually learn different part of the grammar better and different part of the grammar worse, because the git
on the same date when I
on the same data. Or the git sampling is it bound to converge to a global optimum?
No. This particular experiment that seems that it converges to some. It can be global optimum, but I tune this parser only on Czech and English. So after it, I run it on all the languages. So that I tuned means that I switch the models and saw the scores, but. Of course, I can.
So the standard deviation is low. That's
yes, it's quite low.
So actually, what we can do is, if you have, many. That means that if you have many possible combinations? Because you said you tried many models, like, having these fertility separately for left and right, or having them together, including a model, not including a model. But this still seems to me to be a relatively low number of possible combinations, like in the hundreds maybe, but at most, right? So, can you do it? Can you tune it automatically for each language, just running it 100 times and see on some development data how well you do?
Yes.
And then you choose different models for different languages?
I can tune, but I don't know what would be this for, because the task is to be able to parse language for which I don't have the tree bank. And this is something like training on the Go data.
Yes, that's right. I mean, of course, it depends on the application, right? So if you test it in an empty system, you should definitely use the empty system score for saying, which is good for which language. But if you doesn't have any other comparison, I understand you would like to have an objective function which does not depend on the annotated data, right?
Yes.
And you haven't thought about it, right? Which would be the function that would tell you that, for whatever Italian, you should not use one model and just look at the annotated data. You think it's possible?
I don't know. I don't know why to do it.
This is a sort of a related question. For example, when you are doing supervised learning, you don't want to use any development data with annotations and tune on it, because then it's not unsupervised training, right? Were you thinking about running multiple models on the same data in a supervised question, and then somehow to fuse them together, saying that some models, help in some different way, to get good results, to induce the models?
Yes. Of course. It should be the way.
Where it's possible.
Yes.
Did anyone else did it?
No,
No. Because it's still sort of engineering, right? Your hypothesis is that reduction, somehow helps to induce the structure of the language. So the question is, who's going to guess, different, measure, which induce another structure. For example, I don't know, the Spitkovsky inverti proposed his hypothesis about language that induce structure to the language. Or present structure.
no, I don't understand.
No, for me, the reducibility tells you something about the structure of the language, how you can attach, different parts of the sentence. So I guess the Spitkovsky has some similar hypothesis, that assumes something different about the language.
They use only the dependency model variances, as I showed.
Okay,
They have nothing like this.
okay, so this is a completely new thing. So basically, remove the reducibility, you would get something very similar to Spitkovsky.
Not similar, because he used a different model and different he don't use
the dependency model environments, but there's a problem to create the small change has to be simple because it is done well, yeah, there is something like the machine learning part, right? But at the end, what you are using something hypothesis about what defines structure of language, which is the reducibility or the structure of the model. Different people have different ideas about how the model should be used, and how they differ. Just by simply changing, how things are structured into small models, but we depend on text and I guess I'm not clear. Because you have some hypothesis, right? You reducibility. Yes. And this clearly says something about the structure of the language. I guess. This is your hypothesis and you verify that it works. And just because it's something similar, explanation why his model should work. What was his motivation to structure the models he had, the way he did this? I don't know, it's on the motivation is that he used
That's probably the valency model, and they have and
the valency model says that
words generate slots for other words. That's like a generative top-down model for a sentence structure, I would say. Like the story is that you start with a word and it requests for other words. Then they fill its slots and then recursively down in the tree. While here,
for example, in a Switkowski model, there is he has that generating the new child of a node depends on whether this child is the first child, or it is the second or third child. This is one feature of this model, which I don't have here. Because the distance, I have distance here, and I have the number of children. He has a number of children. Here is the stop. Yes, but stop doesn't depend on number of children before. Stop depend on whether it is the current model. So what can you say when more because instead of
kind of slightly more detailed than his, right? Gives you more parameters simply, right?
I think it's similar. Something the filter doesn't have, and something the Spetkowski model doesn't have. In Spetkowski, the DMV, the number of children, I don't have the
adjacency. But instead of the adjacency, again you have much more detailed distribution, which is on the distance, right? Because the adjacency is an approximation of a distance. Adjacency means that if it's just next to it, it gets some different probability, probably higher, right? And if it's not close to it, next to it, it gets some other parameter, but all the same, regardless how far it is. Whereas in your model, you have different parameters depending on the distance. So you have a more detailed model.
yes, I have. Yeah. Okay.
Randomly for the gift sampler.
Yes. I
My question is, do you think 200 iterations enough for the convergence? My assumption is that the convergence may be because of the temperature settings, not because of the global.
it depends on the task. I tested it for the 200 and 500, and it was the same. Yes, it converts, but 200 is enough for this task. 200 is enough, and when you ask for the
word segmentation, they say they are running gift sampler for like 20,000 iterations, then they take samples of it.
yes, because for word segmentation they have much more words. I use only the part of speech tags. I have, for example, 50 part of speech tags. While the segmentation is done on it's very large corpus, and there are word forms or morphemes.
Mainly word forms because the word segmentation.
I assume that there should be more iterations for this task.
Okay, thanks. Did you run multiple times that 200 iterations or okay? That's what you said. variation, yes? Yes. Okay. I have one comment on the comparability with Spitkowski. As far as I know, the expectation maximization algorithm they use is quite time consuming. So they are happy they can run it on the kernel training data set. But the Wikipedia is many times bigger. I don't know what's the exact proportion. It's about, it depends on language, but for Czech it is 20 million words. Okay, so the data that comes from Martin Marish. So I'm afraid they are not able to run the algorithm on Wikipedia text. So the first idea how to make it comparable wouldn't work. And even though if they could, then it would be fair for David experiment to run also the sampling on the Wikipedia text, which also should lead to improvement, but also the Git sampling is also slow unless you parallelize it. I use the reusability feature. It's very time consuming because for us each small change I have to go to all the descendants and they can change. So I have to. It's more complicated. The small change is more complicated if I use the reducibility feature. So I also can train only on less data, like only the training part of the tree bank. Yes, I can, and I can do also the parallel sampling. I try to do the parallel sampling, but I haven't enough time to test it on more data, so. But it's possible to sample the trees in the parallel way, and after each iteration, for example, change the scores between the individual tasks, between individual jobs, and continue sampling. So it's a possibility how to make it
distinguish both, because you have different model, what do you think getting the model is different that helps you in your case? And then, of course, because you have different model, then you have to run different techniques.